Hi, welcome back to my channel. Now this time we will be talking about the polar representation of complex numbers. Hi, welcome back to my channel. Last time we have already discussed about the rectangular representation of complex number. Now this time we will be talking about the polar representation of complex numbers. Okay, so we already know that the concept let's say we're given with a complex z, then let's say z is x plus iy plus iy. Now the magnitude of z, or we say the modulo of z, is actually the distance from the complex z to the origin on the complex plane. So that means the modulo of z denoted by this is actually the square root of x squared plus y squared. And so since this is actually, if you are going to denote this, let's say this is our z, this is our origin here. So that's x plus x and y, the ordered pair. So if we are going to denote an imaginary circle with one of its point is the z, I'm assuming I have a perfect imaginary circle here. Now, this is actually a circle with center at the origin, so this is our radius r. So we can denote the magnitude or the modulo as r here. Also, from this line segment connecting the point on the origin to the point on the complex, to the complex number z, we can project an imaginary line perpendicular to x-axis. Okay? So, since we are talking about the magnitude of the vector z, so might as well we will be talking about the direction that makes up with the positive x-axis. So, we denote this direction, theta, and back in our trigonometry class, we can get the value of the cosine theta with this line here, and we can get the value of the sine theta with this line here. So one of the identities we've learned in our trigonometry that tangent theta is equal to sine theta over cosine theta. So in this case, we have y over x. Okay, so which means that this is our the theta is our direction that makes with the positive x-axis for a given complex number z. Now, with this case, since we're talking about the polar representation, so our z can be written into a polar form or cosine theta and or sine theta, because this is our remember, this is our x component. So this will be our x component here, and this is our y component here, back in our trigonometry class, that we can get the value of the cosine here by taking, we can get the value of x here by taking the cosine of this theta multiplied by the hypotenuse of the triangle formed by this projection. Same, we can get the value of y by getting the cosine of theta multiplied by the measure the length of the hypotenuse of the triangle formed by projection. So remember in trigonometry that we have this theta for a certain triangle, so we can get the value of this side by getting the cosine multiplied by the hypotenuse. It's something like that. Okay, so that is now our polar representation of the complex number z. Now, since we have gotten the value of the theta here, so this is our theta. Now, our theta now will now be our argument of z. But remember, the argument of z, since we're talking about the theta, and theta can be any of the value provided that they would get the same result. So since of course trigonometry on the circle it's always periodic, so the argument of z is not actually unique. So it can be up to a multiple of um 2 pi. So meaning to say that our argument of z, let's say this is the symbol arg z, is our theta plus 2 k pi. Why? Because let's say this is our theta here. This is our theta here. Sorry, this is our theta. This is the same as if we take another revolution, a 2 pi revolution, that's still the same answer. So therefore, our argz is not really unique. Now, to get the unique determination of the angle theta, we would limit our argz to negative pi and pi interval. So in this case, since we are limiting the presentations of argz, so we are now getting the argz. So it's capital. This is what we call principal argument of the complex number z. That's it. Okay. Let's consider for example here to illustrate on the argz. So we have argz. So we have to get the value for argz. Suppose our z is 2 plus I2. So that means this is the same as getting arg of 2, 2. Okay. So remember, this is our x, this is our y. So to get the principal argument of z, I can have it as it's tangent theta of y over x. So that means it's 2, 2. So this is the same as theta equals tangent inverse of 1. And we've learned that in our trigonometry that the tangent inverse of 1 is pi over 4. So that's 45 degrees. So this is actually the same as pi over 4 plus any multiple. So if we are only getting argument of z, so we are actually getting pi over 4 plus a multiple of 2 pi. But since we are getting for the principal argument of z, so we limit this into pi over 4 because it should be on the interval pi to negative pi to pi. That's it. Okay, so note that the real image of z. Okay, so if we are talking if the real image of z is greater than 0, it only means that the principal argument of z here is actually less than pi over 2. Why? If we are going to take the illustration here, this is our pi over 2 here. So which means that if the argument is a principal argument, meaning to say that the direction is found in here, so of course the real image, which is our x, is always positive, because if we go beyond pi over 2, so this is somewhere here, this means that the value of x here is negative. So this makes sense with the remark that when the real image of z is greater than 0, then the absolute value or the modulo of the argument of z is less than pi over 2. That's it. Now, okay, so let's now talk about the idea. Let's suppose, for example, we have z1 equals r1 times cosine theta 1 plus I sine theta 1. We also have z2 equals r2 times cosine theta 2 plus I sine theta 2. Okay, that's it. Now, if I'm gonna multiply z1 and z2 here, so I would have R1, R2. So I should get the value 4. So I should get the value where I can have let's say cosine theta 1, cosine theta 2, and if I'm gonna multiply this with here, that's sorry, why did I write this? So that's gonna be plus I cosine theta 1 sine theta 2, and I would have plus I cosine theta 2 sine theta 1, and finally I would get negative sine theta 1 and sine theta 2. Okay, so I can simplify this as anyway, I can pair this here and this, so I would get cosine theta 1 cosine theta 2 minus sine theta 1 and sine theta 2 plus I, and I can pair this, so I can extract I here and I can pair cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. And what identity is this? This is actually an identity back in our trigonometry. This is the same as okay, let's you just have to review your trigonometry class. This is actually the same as taking cosine of theta 1 plus theta 2. Okay? And this is the same as don't need to. Okay. And this is the same as I, and this is actually the same as sine of theta 1 plus theta 2. Okay, that's it. So what does it mean? Meaning to say that if we take the argument of the product of two complex number, argument of z1, z2, this is the same as taking the sum of the argument. So that's argument of z1 plus argument of z2. And that's it. Now, observe that this is argument, so this is not unique. So this goes up to the multiple of 2 pi. So I can write 2k pi, where k is positive integer. Okay. What does it mean? This means that if theta 1 is one of the values of z1 and theta 2 is one of the values of z2, then theta 1 plus theta 2 is actually one of the values of z1 times z2. So this is now the implication for these polar representations of the product of two complex numbers. Now, this is our argument of the product of z1 and z2 here. So that is actually up to a multiple of 2 pi, because of course argument is not uniquely determined. We can just write this as well as argument of z1, z2. That's argument of z1 plus argument of z2 mod 2 pi. That's it. Okay, so let's consider this way. Suppose we have z equals negative 1 plus I squared of 3 all over 2. So to solve for z squared, we would have negative 1 plus I squared of 3 all over 2. squared. So if you do the manipulation, you can have negative 1 minus negative I squared of 3 over 2. Okay, so, okay, you just have to multiply negative 1 plus I squared of 3 all over 2 by itself, and you would get this, pretty sure. Okay, now how to get for the arc of z? Observe that our y here for the given z. Okay, let's go it this way. Our y with respect to z is square root of 3 over 2, and our x with respect to z is negative 1. So we would get 3 over 2 all over negative 1. So to check back on our basic trigonometry, that is square root of 3, so that's actually pi over 3. Supposedly, but this is negative 1, so that's belong to the negative x-axis. So somewhere here is our negative pi over 3. But since we start from here, so therefore it should be the angle here. That's pi over 3, that's 2 pi over 3. So the arc z is 2 pi over 3. For the arc z squared, if you notice, this is actually a negative. So that's negative 2 pi over 3. So therefore, the identity would say that the arc z times z is the same as arc z plus arc z minus 2 pi. So okay, so let's consider these two here. Z1 equals 1 plus I, and Z2 equals square root of 3 plus I. So observe that Z1, I can write it in this way. Our R here is square root of 2. And the arc of Z1 is, so the theta here is pi over 4. So instead of writing any form, I write this in this way. E to the I pi over 4. And I can write Z2. R for Z2 is square root of 3 plus 1, so that's 2. So I shall write this as 2 e to the, that's 1 over square root of 3. So basically that's pi over, when x is square root of 3, so the pi over 6. Okay, that's pi over 6. Now, since I know that this is how I write z1 and z2 in this manner, so the product of z1 and z2, I can write this as 2 square root of 2 e to the I pi over 4 plus pi over 6. And so I have 2 square root of 2 e to the, what's pi over 4? That's 12, so that's a 3 pi plus 2 pi, so that's 5 over 6, 5 over 12. So e to the I 5 over 12 pi. Okay, now to take the argument of this, I'll just solve this first when z1 is divided by z2. So I would have square root of 2 over 2 e to the I pi over 4 minus pi over 6. So would get 3 pi minus 2 pi, so that's 1. That's 1 over 12. So this is square root of 2. So anyway, I can write square root of 2 as, anyway, that's it. So that's square root of 2 over 2 e to the I pi over 12. So what's the implication then? So in this particular product, I would have arg of z1 times z2 is just the same as arg of z1 plus arg of z2. And another thing is for the arg of z1 over z2, that's the same as arg of z1 minus arg of z2. So this is now our additional property for a specific type of this calculation. Okay, so let's consider example here. I would have, let's say, negative square root of 3 plus I, and I would have here 1 plus I all over 1 plus I squared of 3, something like that. So in order for us to solve that, we will have to use the identity we've done earlier. So in this case, what I'm gonna do is I will denote this first here as z1, I'm gonna denote this as z2, and I'm gonna denote this as z3. So in this case, our z1 here is negative 3 plus 1, negative square root of 3 plus I rather. And so the R1 here, so I'm gonna denote R1 for the modulo of Z1. So this is the same as 2. So I'm gonna take the square root of square root of the square of square root of 3 plus the square of 1. So I'm gonna have 2. And solving for the theta here. So observe that this is my y here is 1 and my x is negative square root of 3. So you may check that on your trigonometry class that's negative pi over that's pi over 6, negative pi over 6, or negative 30 degrees. So this is the same as pi over 6. So I'm not gonna I'm sorry, I don't have to say it's negative pi over 6, but pi over 6 rather. Okay, because why? Because it's the same as 30 degrees, but with respect to the negative x-axis. So that's gonna be 5 pi over 6, because that's equivalent to 150 degrees. So that's pi 1. And so for z2, the modulo of z2, so that's 1 here. My z2 is 1 plus I. So I'm gonna have my r2 is square root of 2. And so my theta 2, if you notice, this is 1x and the x is 1, the y is 1. So this is very obvious, that's pi over 4 or 45 degrees. And so I have z3, so that's 1 plus I squared of 3. And so this is having y equals square root of 3 and your x is 1. So this is obviously pi over 3. That's 60 degrees. Okay, so therefore this is the same as if I'm gonna write this as 2 to the e I 5 pi over 6 times square root of 2 e to the I pi over 4 all over, that's e oh, by the way, for R3 here, that's obviously 2. So I'm gonna have 2 times e to the I pi over 3. So cancel this one out and square root of 2. So if I'm gonna add this here and subtract this by pi over 3, I don't have to do algebraic manipulation, because this is not algebra we're talking about. So this is the same as 3 3 pi over 4. That's it. So this is all for now. So if you have question, you can comment down there on this video, on the comment section of the video, and you don't have to worry because there will be part 2 of this topic, which I will provide a lot of explanations and a lot of examples before we can proceed for the next round. That's it. So for those who are new to my channel, you can subscribe for more updates for the continuation of this part, and you can also check on some of my videos I have uploaded on this one. Thank you so much for listening. Have a great day.